Today, let us try and understand what actually happens if the resistive load is replaced by an inductive load.
Hello people and welcome to Electronics for All. This is a channel where we will design and develop industrial grade electronic systems. For every system or a circuit, we will start with basic fundamentals or textbook explanations. In the second step, we will confirm the functionality via simulations and calculations. This stage will progress into development of a prototype. The prototype will then be subjected to rigorous testing to prove its ruggedness. So you will get a walkthrough of electronic systems developments with best industrial practices. So let us start.
In the previous video, we observed that when a MOSFET is triggered via PWM pulse with a resistive load, then one can obtain a variable voltage and in turn variable current in the circuit. This variable voltage and variable current is directly proportional to the duty cycle of the pulse width modulation pulses given to the MOSFET. As we increase the duty cycle, the voltage across the resistive load can be increased, which in turn also increases the current in the circuit, and upon decreasing the duty cycle, the voltage across the load and current in the circuit decreases. Today, let us try and understand what actually happens if the resistive load is replaced by an inductive load. So let us go to MATLAB software again and switch to Simulink, where we will again develop a Simulink model. We will energize an inductive load via a DC source and a MOSFET, and the MOSFET will be fired by PWM pulses. Let us open Simulink library browser and search for DC voltage source and add it to the model. Remember, the shortcut to adding any element from this library browser is Ctrl+I. Apart from the voltage source, we will require series RLC load, MOSFET, which can be found in specialized technology, DC voltage source for measurement of voltage across the load, also a block for current measurement which will measure the current in the circuit. A power GUI block which is necessary here, a pulse generator which will generate firing pulses for MOSFET. Now let us go ahead and make the connections. Before connecting all the elements, let us disable the measurement port of the MOSFET, and after that we will convert the RLC load to L load by double clicking it and making proper changes. We will use an inductor of 100 nanohenry. Now let us align the inductor vertically with the MOSFET by rotating it. To rotate any component, you need to first select it and then press Ctrl+R. Now let us connect and make a loop such that MOSFET is connected to the DC voltage source via the inductor. In between the inductor and the DC voltage source, there will be a current measurement block that will measure the loop current. The specifications of the pulse generator are such that it will be operating at 20 kHz frequency. Hence, its time period will be 1 divided by 20,000, which we will input into the period field. Its duty cycle will be 80%. Now let us connect it to the gate of the MOSFET. With some proper alignment. The voltage measurement block will be placed in parallel with the inductor to measure its voltage profile, which will be observed in the scope. Yeah, so we forgot to add the scope. Let us add it from the library browser. change the number of axes, double click on the scope to open it first and click on this gear icon to enter the configuration wizard, and instead of this 1, change the number of axes to 3. Connect the first input of the scope to the pulse generator, second to the voltage measurement block, and last to the current measurement block. We will have to change the simulation parameters first. This can be done via Model Configuration Parameters option found in Simulations menu. Here we will change the solver type to fixed, and we will use 10 raised to minus 7 seconds as fixed step size, and solver will be ODE4. We will repeat the same settings in the configuration of Power GUI parameters. The simulation type will be discrete and the solver type will be touch-in. Keep one thing in mind, that the sample time here has to be the same as the fixed step size as used in model configuration parameters. Let us reduce the simulation time to 0.0005 seconds or 500 microseconds. Also, we will reduce the RDS(on) of the MOSFET to 1 milliohm. Now, before running the simulation, let us first investigate the behavior of the inductor theoretically. Now, the equation of the voltage across the inductor V is equal to L di by dt, where V is the voltage across the inductor, L is the inductance value, and di by dt is the rate of change of current. To find the current profile, let us shift L to another side and integrate the equation. Integration will produce an equation as shown. According to the equation, the inductor current will keep on increasing linearly until the MOSFET switch is on and will reach its maximum at T on. But when the MOSFET switch is turned off, the inductor will behave as a source and will discharge its stored magnetic field via the body diode of the MOSFET, and the direction of the current will be negative. Let us confirm this via the current waveforms of the inductor in the scope. As we can see here, the inductor is charging and the current through it is increasing in linear fashion and reaching its maximum at T on. And during the off period, the current is actually negative because the direction of the current has now reversed and the conduction is taking via the body diode of the MOSFET. So this much will be all for today's video, guys. We have seen how actually an inductor behaves when it is energized via a MOSFET running on PWM. In the next video, we will see how a coupled inductor works when it is powered via a MOSFET in the same fashion.
Thanks for watching. Drop a like if you found this video helpful. Leave a comment if you have any query regarding the topic. And don't forget to subscribe and share this video with others.